Welcome to session number 44. This will be our last session on the MOS field effect transistor. And in today's session, we're going to be reviewing what we did in the last session, this threshold roll-off. We'll be looking at its, I guess what you call kissing cousin, which is the narrow width effect. So in the threshold roll-off, we have small L. In the narrow width, we have small w, and we'll see that they actually have opposite effects to threshold. And then we'll be looking at two more second order effects, DIBL and GIDL, and we'll see what that's all about. We'll probably just quickly review the evolution of the inversion charge and IB relations as we go from the simple theory to the more complex theories, and hopefully I'm going to try to make time to do some worked examples. We'll begin today's session with the conclusion to Mozart's overture to the Magic Flute, and you'll see the different faces of people, the idea that the beauty of Mozart's music brings all of mankind together, and we'll see you in about 3 minutes. Welcome back, and here are a few of the topics we'll be covering in today's session. We're going to start with the short channel effect. By channel, I mean a short L. And we covered that a little bit toward the end of last session. When the L goes down, the threshold voltage goes down, and the gate loses control over what happens in the inversion process. Not so good. And then we're going to be looking at its, I guess you call it kissing cousin. When L goes down, generally W goes down. But when we scale the devices to make them smaller, both L and W go down. So we'll see what happens when W goes down. And we'll see that it's exactly the opposite of what happens when L goes down. The threshold voltage goes up, and that's a good thing. And then we'll move on to something called DIBL and GIDL. DIBL is drain-induced barrier lowering, and GIDL is gate-induced drain leakage. And we'll see that these, like the short L and the narrow width effect, these two effects are somewhat complementary, not quite as complementary, but they both involve the drain. One is drain barrier lowering and the other is drain leakage. Then we'll go on to very briefly to talk about the evolution of the Q inversion and the IV characteristics. And by say evolution, we will go from the very simple theory up to the more complex and comprehensive theories. And then finally, we'll be doing some examples from Chapter 23, which is the chapter of worked problems in MOSFETs, and we'll be ending with a aria from Rossini's La Cenerentola. So let's get started. So just in the way of review, at threshold, we have the depletion region under the gate reaching its maximum value. However, we also have source and drain contacts. These contacts are N+ degenerately doped, so that we have a PN+ junction. So if we have a PN junction, we have a depletion region. And the depletion region falls entirely on the P side because the P side is lightly doped. Even if we have 10 to the 17th doping on the P side compared to 10 to the 20th doping in the degenerately doped contact, it is lightly doped. So the entire depletion region falls on the P side, and it has a depth of WD. And it falls not only outside the gate, it falls into the gate. So we have negative ions. These are negative phosphorus ions that have accepted an not phosphorus, excuse me. These are negative arsenic ions that have accepted an electron and become negative. And they extend into and underneath the gate region. So under the gate region, we have negative ions which are controlled or produced by the positive voltage on the gate, and we have external ions which come from the N+ source. So the Q depth now is composed of Q depth 1 from the gate and Q depth 2 from the external PN N+ junction here. So this is the this here would be the Q depth 2, and this is the Q depth 1. So now the Q depth 1 part, which is controlled by the gate, is less than it would have been without Q depth 2. So therefore, Q depth goes down, and therefore the voltage goes down, and specifically the threshold voltage goes down. And that is what we mean by threshold voltage roll-off. As L becomes shorter and shorter, the threshold voltage becomes lower and lower, and it gets worse when VDS is greater than 0, because when VDS is greater than 0, we have a positive voltage at the drain, and therefore we are reverse biasing this PN junction, and this red line goes down even further. So this slanted line here becomes even more slanted, and the effect gets worse and worse, as these negative ions work their way further and further underneath the gate. So that's why this line here for VDS greater than 0 is actually worse than for VDS equal to 0. Of course, you don't have to worry about the source because we don't put a voltage at the source terminal. Okay, so this is what we found for the figure of merit, and there are two parameters here. It's always, by the way, I should always say it is less than 1 if x sub j and if x sub j and WD were both 0, then the figure of merit would be 1. How do we make the figure of merit closer to 1? We make xj as small as possible. That's a good thing by making a shallow implant, and we make WD as small as possible by increasing the doping. So that is really a big deal. And these are both under our control. Shallow implants are good, and increased doping is also good. However, we are going to make L smaller. That's what scaling is all about. Everything gets smaller, and L gets smaller, and also, fortunately, W gets smaller. So what we've done here is we've taken this guy and we've rotated it in the plane 90 degrees. So if you look here, this would be W, this distance into the board or into the paper. And that's shown here. We've rotated it 90 degrees now so that L is into the paper, and we have W shown as a horizontal line. Well, now what we still have the gate, and the gate has a voltage on it. It's generally positive, so the lines go down, electric force lines go down, but as W gets smaller, there is a fringing field. There is a field which exists outside of the gate due to the gate, but it does not go into the depletion region. It is the fringing field which becomes more and more important as W becomes smaller and smaller. In fact, you could take it to the limit. If W was just a point, then there would be no vertical lines at all, and everything would be a fringing field. So now we can write Q dep is equal to Q dep 1, which is this spot right here, the vertical lines which go into the depletion region, minus Q dep 2, the depletion part which, due to the fringing field, which does not contribute to the gate depletion region at all. So in order for the threshold to take effect now, we have to increase the gate voltage to compensate for Q dep 2. So if we look at the threshold voltage as a function of W, as W gets smaller and smaller, the threshold voltage gets larger and larger, generally not dependent upon VDS. So we have two issues here. One where the gate voltage, where the threshold voltage goes down, the other where the threshold voltage goes up, and they essentially compensate for one for another. So that's actually a pretty good thing. So that's why we grouped the short channel effect, the L effect, the threshold voltage roll-off, with the narrow width effect, because they essentially are kissing cousins and they do the opposite thing. So that's a good thing. All right, now we'll talk about the next set of two, which are drain-induced barrier lowering and gate-induced drain leakage. Now, the way I like to remember them is in their acronyms, which are DIBL and GIDL. And if that sounds like a comedy team, it probably it does. Actually, I like to think of it more as a law firm. DIBL and GIDL. Well, anyway, so both DIBL and GIDL are generally lumped into short channel effects. DIBL is certainly a short channel effect. GIDL is somewhat less so. Well, anyway, let's talk about DIBL first. But before we get into the particulars, I just want to make a point about the drain versus the source. The drain is the more important contact. They say in Vegas, what happens in Vegas stays in Vegas. What happens in the drain affects the entire structure. What happens in the drain affects the source, the channel, everything. The drain is a big deal, and a lot of effort is going into engineering the drain so that we can make an optimal performance. So we're going to take a look at the energy bands along the channel in the Y direction, and we're going to start with no VDS, no voltage on the drain, and let's start at flat band. And I want to find out what this barrier height is if I'm at flat band. So the gate is N plus silicon, degenerately doped N-type silicon. The P is 10 to the 17th. So we have a barrier of, well, if it's N plus, so the Fermi level is right at the conduction band. So we have a starting barrier of about 0.56 volts, and then we add that to the barrier from the P, considering this like a P, an N plus P junction. So we have 0.56 plus 0.42, or about 1 volt. So the barrier here underneath the gate would be approximately 1 volt. If we had flat band. Well, flat band is not realistic, so let's go to now a realistic case, and a realistic case would be, say, weak inversion, somewhere between weak inversion and moderate inversion. If we had it such that the surface was intrinsic, then the barrier would be 0.56. So that would be the parameter A. That is also a little bit too high. So let's go with a reasonable weak to moderate inversion. Now let's say A is about 0.3 volts. So if we increase VG, then the barrier will fall. It will fall from A to B. So if we have weak inversion with barrier A, if we have a more positive voltage or VG, then we would get a barrier height of B. In both cases, we have depletion regions underneath of the surface, and because we have no voltage on the drain, this barrier height is horizontal, and it is the same for the source as it is for the drain. There's complete symmetry now between the source and the drain. That will not be the case, of course, when we put on a voltage on the drain. The other thing is we have a depletion region under this N plus P diode, and we also have a depletion region over here, but that's not nearly as important. This is the important depletion region because when we put a bias on the drain, we're going to increase this depletion region at the drain contact. So even if we had no VDS, we had no bias on the drain, there are some lucky electrons, quote unquote lucky, especially with a lower barrier, which are able to surmount that barrier, and they would see no electrons over here. So any electron that comes in at the source, they see no electrons over here, and they're able to move relatively slowly, kind of meandering along from the source to the drain. And of course, they would move by way of diffusion. And that would be true for a short channel as well as for a long channel. Now, when we add a VDS, this adds a new wrinkle to the picture. So let's take a look at adding now a VDS for the long channel device. It is no longer now in equilibrium. The depletion region has increased, so the distance from here to here with a VDS is larger than the distance from here to here without a VDS. So we have a bigger depletion region. We have now also a reverse current because we don't have equilibrium anymore. So we have a reverse current between the N plus and the P substrate, but that is relatively minor and we can disregard it. But because we have a disequilibrium now, we have a Fermi level which is discontinuous. And where does the Fermi level drop? It drops across the point of high resistivity, and that, of course, is the depletion region. So we have a discontinuous Fermi level because we no longer have equilibrium, and we have a VDS drop across the depletion region. Well, what has changed? At the source, nothing has changed because the source is basically still isolated from the drain in a long channel device. So any lucky electron can still move by way of diffusion. Now, I've drawn this line here, not quite horizontal. Here it is completely horizontal because there is no electric field from the drain to the source. However, when we put a VDS, now we have a field which goes from right to left, which sucks up electrons electrically from the source to the drain. So that's why this line is slightly skewed, a bit lower on the right side than on the left side. But clearly, this is the big deal right here. We have a lowering of the barrier on the right side and the drain side compared to the source. We have this conduction band that's now lower. That's always the case. Whenever we have a positive voltage on a p-n junction or any silicon, the bands are lowered. So far so good. We haven't really changed too much. We might have a little bit more drain current due to this very relatively minor electric field that exists along the channel, but everything changes when we have a short channel. So this is the long channel and this is the short channel. So when we have a short channel with VDS equals 0, we have this increased depletion region on the drain side, which encroaches well under the gate. So it's not only vertically on the drain, it also moves along the gate. And now we have a situation where what happens at the drain affects the gate. It doesn't stay at the gate because we have this depletion region, which is in the horizontal direction as well as in the vertical direction. Exactly the same thing that we saw in the threshold roll-off. So now we have a barrier lowering not only at the drain region, but also it's starting to affect the source. So the upshot is that even for relatively small values of VDS, we're going to have a significant effect of the drain on the source if the L is really small. So for small channel lengths, L, this is a huge deal. Now we can evaluate this. We can actually find out what the shape of this is, which is kind of interesting because the analysis is in two dimensions. It's in the vertical dimension, which we call X, and it also has to do with the along the channel. So it's requires two dimensions, and the Poisson's equation turns into a partial differential equation in two variables, x and y. The analysis is certainly more challenging, but it's doable, and there are papers where you can read all about that. So, again, the bottom line is that even for moderate values of VDS, we have a significant impact of the drain on the source, and if we have a situation where the barrier height at the source becomes less than, say, 0.1 volts, then there is essentially no barrier, and the drain voltage VDS controls the current. We no longer have a transistor. The gate no longer controls the IDS, the drain current. The drain current only is controlled by the drain voltage. That is not a transistor, that is a resistor, and that is extremely bad. So that is the deleterious effects of DIBL. And that, how do we ameliorate it? How do we make it less? One thing we can do is reduce this depth. This remember, for the threshold voltage roll-off, this was the what we call X sub J. And the other thing is increase the doping. Increases the doping, reduces the depletion region at the drain contact. Exactly the same thing that we saw for the threshold roll-off. So here's the bottom line. Again, another bottom line. I guess you could say with each new generation, W and L are reduced. VDD, which is basically the power supply voltage on the drain, is Tox, and the contact depth, the X sub J, are all decreased, and doping is increased. So that is essentially, in a nutshell, what scaling is all about. There are a few other aspects to scaling, but those are the main things. Decrease W, decrease L, decrease the drain supply voltage, decrease Tox, that's a big problem, and decrease the drain and source contacts, and increase the doping. So how short is the channel length for DIBL to become important? Well, if the DIBL is such that or I should say, if the channel is such that it's equal to the depletion regions at the source and the drain for even a moderate value of VDS, then L is too short. And generally, 500 angstroms or so for drain lengths would be susceptible to DIBL. And just one more point about DIBL before we go on to GIDL. It's really not that big a deal as far as the particular place that we're at, whether it be weak inversion or moderate inversion. It's over a fairly large range of gate voltages. The real issue is the channel length. So if we had a weak inversion, the barrier would be, at the source, would be higher initially, but once that depletion region starts encroaching, if the L is short enough, that barrier goes away. And for moderate inversion, the starting barrier will be lower, so it might take a little bit less VDS for it to disappear, but it's still, even for weak inversion, it's still going to be a significant issue. So the main parameter, the main point that we have to consider for DIBL is the channel length. It is really truly a short channel effect. Now, GIDL is generally lumped with DIBL because they both have drain associated with them. In the GIDL, we have gate-induced drain leakage, whereas in DIBL, it's the drain which causes the problems. And let's see what's going on now. It's not necessarily a short channel effect, but because it involves the drain contact and weak inversion, we generally like to, I like to lump it in with the DIBL, beside the fact that it rhymes, which is another big deal. Okay. So, if we are in weak inversion, we expect that the current will be small, and the weaker we are in inversion, we expect that the smaller the IDS will be. So as VG decreases, so we go from threshold to moderate inversion to weak inversion, as the gate voltage decreases, we should see a exponentially decreasing IDS. That's not what we observe, especially for really weak inversion, not so much in moderate inversion. In weak inversion, almost close to depletion, we see an increase in IDS, and that is a disaster. So let's go back to figure 2235, where we have a quite weak inversion, which means that we have a big barrier and we have a relatively large VDS. So there's two bad things that happen here. The large barrier means that we will get a relatively close contact between the valence band and the conduction band, and the high VDS means that we have a possibility of having an electron being able to jump from the valence band into the conduction band. So everything is focused on the drain with a relatively large depletion region. So VDS is pretty healthy, and the valence band is close to the conduction band because the barriers are high and the bands are extremely steep. That is the problem. And without going in too much into the detail, I don't know if there really is a significant mathematical model which can predict exactly what this effect is, but we have a curve. So in strong inversion, if we plot the log IDS versus the gate voltage, we have relatively flat, especially over in the ID SAT region over here. And then as we get into weak inversion, we have a straight line. The structure is susceptible to DIBL, or basically between threshold and moderate inversion down into weak inversion. When we get into very low weak inversion, we start seeing this increase in drain current due to the fact that electrons are able to jump from the valence band into the conduction band. And it's actually worse than that. Of course, once they jump, then that is that's a current. That's IDS. So this guy right here represents the current which exists at the drain, and of course that goes to the external circuit. But it's actually even worse than that, because when the electron jumps from the valence band into the conduction band, it leaves behind a hole. So it leaves behind a hole, then this, of course, is p-silicon, but p-silicon still has quite a number of minority electrons. So those minority electrons jump into the hole, and this creates substrate leakage. So we have leakage due to jumping from valence band to conduction band, and we have leakage due to electrons jumping into holes. A really, really bad situation. This guy is supposed to continue going down and basically going to zero, and unfortunately it does not. So GIDL and DIBL are two really serious issues. DIBL we deal with, again, by making shallow contacts, engineering our drain, and increasing the doping. GIDL is a very difficult problem to deal with. Okay, so the next section we're going to run through very quickly. It's a pure review, and you can certainly look at the equations, and they should be quite familiar. Equation 2271. So what do we see if we see this equation? Well, the first thing we notice is there's no channel voltage. So this cannot represent a field effect transistor. The minus sign is because it is an NMOS type of device. This generally would be written for a MOS cap. A MOS cap, there's no channel voltage, so this is the equation that we would have in strong inversion for a MOS cap. So we should never think of this as being any starting point for analysis of a field effect transistor. So I call this the super simple theory, and it does not allow for basically for anything, so it's not terribly useful. The simple theory, we include the channel voltage, and if we include the channel voltage, we get the square law. And of course we get things like VD-SAT and ID-SAT. But it does not include the effect of increased depletion region along the channel. And for that, we look at equation 2273, which does include the increase in channel voltage. This is minus, as minus is plus, and then of course the alpha here represents an increase in negative, that's why the minus sign, in negative depletion region across the channel. So as the channel voltage increases, the inversion charge decreases and the depletion charge increases, and that's what gives us our 3/2 effect for the ID-SAT and for the VD-SAT. Or the VD-SAT is reduced a little bit, and IDS has the 3/2 rather than the purely square law. And finally, and this is a very practical issue, we have back biasing on the substrate, always using a reverse bias on the substrate so that we increase the threshold, and that is this term right here. These two terms are lumped into the famous M value. The alpha is proportional to this K value that we looked at way back in chapter 21. K's on the order of 0.3 or less are reasonable. M's, which are unitless, we'd like to see it well below 1.2. 1.1 would be ideal. And then we have the issue of the body substrate, which actually increases the threshold. So that's just way of review. And if we look at the current voltage relationships, then the assumption is that mu is a constant along the channel. Not a great assumption, but we have to live with it because otherwise it becomes relatively complex. There is no recombination along the channel, which means that the current is constant. Nothing's lost. I would say nothing's gained. Obviously nothing's gained. You don't create charge along the channel, but we don't lose any charge along the channel. And that means the current is constant. And in strong inversion, the current is only due to drift. In weak inversion, it is generally due to diffusion. And as we transition from weak to moderate to strong inversion, the current goes from diffusion to a combination of diffusion to drift, and then wholly to drift in strong inversion. So these are the basic equations that we have, and it's not, this is all in the way of review. Okay, so now we're going to go to work problems from chapter 23. Okay, so there are 10 problems in Chapter 23, and I picked out 3 of them, which are more or less standard fare, so hopefully they won't be all that difficult. Okay, so this is the equation that we derived. This includes the increase in depletion charge along the channel. So as the inversion charge goes down, the depletion charge goes up, and we get an IDS, which is a little bit less than we had in the square law. It's actually the 3/2 power. Okay, so the question tells us, show that this equation, which is this equation here, reduces to this equation, which is the small VDS equation. This is in the linear region. So when the drain voltage is small, we want to show that this equation reduces to this equation. Now, we can't go backwards. We can't say, okay, if VDS is large, then the square law reduces to this, because this is the improved theory. So this is the right theory. However, for small VDS, maybe, we're not sure, that's what we have to show, that the improved theory, the bulk charge theory, reduces to the same equation that we get for the simple theory for small VDS. And that makes sense. It should, because for small VDS, we don't have an increase in depletion charge across as we move across the channel. The only time we have that increase in depletion charge is when we have a big VDS. Specifically, VDS is on the order of VD sat or above. So let's see if this guy reduces to this guy for small VDS. Well, the first one, we have 2 terms. There's the first term, and here is the second term. So the first term is pretty straightforward. For small VDS, we just reduce this, we just basically cross this out, and we have VG minus 2phi-B minus VDS over 2. We cross this out, and here we have just VG minus 2phi-B. So that's pretty straightforward. Now we have to take a look at this guy right here. So this guy is not quite as straightforward. So the way we handle this thing is we expand it in a binomial expansion. So this is the binomial expansion. X plus y in parentheses raised to the n is x to the n plus n, x to the n minus 1 y, plus a bunch of other terms which we're going to neglect if y is small compared to x, which is what we're going to claim here, that the VDS is small compared to 2phi-B. So we can expand this into binomial expansion, keeping only the first 2 terms. Now, if it didn't work out in the first 2 terms, we stick on a 3rd term. If that didn't work out, stick on a 4th term. It would get messy pretty fast, but at least eventually, hopefully, we would get there. So we take this guy, which is this guy right here. This term right here, and we expand this guy in a binomial expansion. So x is the 2phi-B, and y is the VDS. So it is 2phi-B to the 3/2 plus n, which is 3/2, times x, which is 2phi-B, to the n minus 1. 3/2 minus 1 is 1/2 multiplied by y, and then we just tack on the minus 2phi-B. These guys cancel out, and we just get the middle term. So we rewrite the whole thing. This is the first term, and now this is the second term. And you see the second term is quite a bit easier, quite a bit more compact than the second term here. All of this thing reduces to just 1 term, which is right here. And then we rearrange this, grouping the terms with VDS. Here's a VDS, and here is a VDS. And this is the same coefficient that we had in the original equation, so we just drag that along. That's no big deal. And let's see where we're at. Okay, so this is the term with the VDS. Well, what is this guy? This is just V threshold. That's all that is. We recognize this as V threshold, so it's VG minus V threshold multiplied by VDS with the same coefficient, and that is exactly what we wanted to show. So I guess you say QED, that which was to be shown has been shown. So that was fairly straightforward, hopefully. Okay, so before we go on to the next problem, there's one little caveat here, which is stupid me. All of this guy, this whole thing, should be in parentheses because the coefficient multiplies everything. So I will make it a point to put all of this guy into the another bracket here. Oh, okay. I always do things like that. All right. Problem 23.7. We have an NMOS device or NMOS structure, which is to say we have a P silicon, which is inverted, and the gate oxide thickness is 100 angstroms, a little bit on the thick side, but not too bad. Doping is our default doping of 10 to the 17th per cubic centimeter, and the gate voltage is 2 volts. So we want to, using the improved theory, the bulk charge theory, and this time we're going to use the parameter K, and they ask us to calculate the saturation voltage, VD-sat. Well, whenever we have a gate oxide, the first thing we do is calculate the areal capacitance, Cox. So there it is, just the permittivity of the oxide divided by Tox, which is 10 to the minus 6 centimeters, that's 100 angstroms. And notice now that we're using the 4, this is the permittivity of oxide, not of silicon, and this is the permittivity of free space in CGS system. So we get 3.5 times 10 minus 7 farad per square centimeter. So now we go back to chapter 21, question 21.13. We put in K, and we can calculate K because we know the doping, we know the epsilon. This is the epsilon for silicon, that's 10 to the minus 12th. The permittivity for silicon, relative permittivity, is about 12. And so we put all that in, we find that K is about 0.36, a little bit on the high side. And the reason is because the Cox is a little bit lower than I'd like it to be. This should be hopefully about a factor of 3 less, which would, or maybe 2 less, which would produce a smaller K. But 0.36 is still reasonable. So now that we have K, we have everything we want. We just put in equation for VD-sat from equation 21.15, and we calculate that VD-sat is 0.56. The effect of the K is 0.6. So if we did not include the increase in depletion charge along the channel, we would have had 1.16 volts. Quite a difference from 0.56, almost twice as large. So it's really important to use the quote-unquote improved theory or the bulk charge theory. Okay, so this is problem 23.10. This is the last problem, I believe, in chapter 23, and here we're given the fact that we have a MOSFET, and we're given the threshold of this particular MOSFET is 1 volt, a little bit on the high side, but not too bad. It's the gate voltage, which at threshold is 1 volt. And we're also given that it exhibits a subthreshold swing of 100 millivolts per decade, and that's a bit on the high side. We prefer it to be more like 70 or 80, but that's what the problem says. This is the inverse of the slope of the log of IDS versus gate voltage, and we are told that the drain current at threshold is 1/20th of a microamp, and we are asked to calculate the leakage current when the gate voltage is 0.5 volts. Well, because we're asked to calculate the leakage current below threshold, we can infer without too much doubt that this is an NMOS device, because the gate voltage goes down from threshold, we go into weak inversion. Okay, so let's see if we can do that. Now we have in weak inversion, which is here. I'd like to calculate the IDS2 when the gate voltage is 0.5 volts. This is the condition that we are given. We are given that the threshold is 1 volt. At threshold, the IDSI is 0.05 microamps. We're also given VG2, it's 0.5 volts, and we just want this guy. So it's pretty straightforward. We just use the definition. Subthreshold swing is the change in voltage divided by the change in current, given the fact that the change in current is a logarithm. And notice that this is the inverse of the slope. The slope would be current over voltage. The threshold, subthreshold swing is voltage over current. So we're given V1 and V2. We are given the log of IDS1, and this is the guy that we're trying to find. So we just substitute in what we have for V1 and V2, as well as for IDS1. And this is the only thing that we don't know. So we're given that the subthreshold swing is 0.1, 100 millivolts per decade. So we just simplify that. And here is this expression. So we put this on the upstairs and multiply each of these by 0.1. And we have relatively straightforward. 1 minus 0.5 is 0.5. We solve for this. 0.1 log IDS1 is minus 1.23 because we bring this over here. And the minus sign comes from the minus sign here. And we get that IDS1 is 5 times 10 to the minus 13th amperes. How many microamperes is that? Well, we take away, say, 10 to the 6 or microampere. So we are still at a tiny, tiny value of current. But unfortunately, it's not zero. So if we have 1 billion transistors and they're all pulling this amount of current, ouch, that's why my laptop is hot. Because each one is small. That's really small. But you add them all up, they say $1 million here, $1 million there. Eventually, you're talking real money. 10 to the minus 13th here, 10 to the minus 13th there. And eventually, you're talking some real current and some real heat. So that does it for the MOSFET. We are finished with the MOSFET. We're going to have just a couple more sessions where we talk about some novel devices and some rules for drawing energy band diagrams, and we'll talk about the high electron mobility transistor. But we should be very proud that we have reached the end of our journey into MOSFETs, and let's celebrate with a aria from Rossini's Cenerentola. And we did one aria previously. Remember, in Cinderella, as it's portrayed by Rossini, there are 2 wicked stepsisters, and instead of a wicked stepmother, there is a wicked stepfather. And the reason is this is opera bouffe, this is comic opera, and it's much easier to make fun of men than it is to make fun of women. So in this aria, we see the 2 stepsisters who confront the prince and his servant, except that the prince is dressed as the servant, and the servant is dressed as the prince. And the servant, who is portraying the role of the prince, looks at the two women and he says, "Una sposa, I can only marry one of you." And then they said, "What happens to the other one? Vulture, vulture." And he says, "Well, the other one I'll give to my friend here, the servant, who's really the prince." So it's a lot of fun, and let's enjoy this wonderful aria from Rossini's La Cenerentola, and we'll see you next time.
Zitto, zitto, piano piano, senza strepito e rumore. Zitto, zitto, piano piano, senza strepito e rumore. Delle due quale l'umore, esattezza e verità. Zitto, 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 piano piano, piano piano, senza strepito e rumore, senza strepito e rumore. Delle due quale l'umore, esattezza e verità. Zitto, zitto, piano piano, delle due quale l'umore, esattezza e verità. Esattezza, esattezza, esattezza e verità. Esattezza, esattezza, esattezza e verità. Esattezza, esattezza, esattezza e verità. Sottovoce a mezzotono, in estrema confidenza. Sottovoce a mezzotono, in estrema confidenza. Sono un misto di insolenza, di capriccio e vanità. Sottovoce, 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 sottovoce. In estrema confidenza, sono un misto di insolenza, di capriccio e vanità. Sottovoce, sottovoce, sono un misto di insolenza, di capriccio e vanità. Di capriccio, di capriccio, di capriccio e vanità. Di capriccio, di capriccio, di capriccio e vanità. Di capriccio, di capriccio, di capriccio e vanità. E Lidoro mi diceva che una figlia del barone, il maestro un grande stone, che quando non si dà. Lidoro mi diceva che una figlia del barone, il maestro un grande stone, che quando non si dà. Zitto, 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 sono un misto, piano piano, piano piano, di insolenza. Zitto, 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 di capriccio. E Lidoro mi diceva, e vanità, il maestro un grande stone, che quando non si dà. Se le sposi pur chi vuole, seguitiamo a recitare, dove vere va d'errore, ma conviene dissimulare. Se le sposi sono vere, chi vuole, va d'errore. Zitto, 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 sono un misto, piano piano, piano piano, di insolenza. Zitto, 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 di capriccio. Alidoro mi diceva, e vanità, il maestro grande storia, che qua non si fa. Se le sposi pur chi vuole, seguitiamo a recitare, dove vere va d'errore, ma conviene dissimulare. Se le sposi sono vere, chi vuole, va d'errore. Zitto, zitto, sottovoce, piano piano, sottovoce, zitto, zitto, ma conviene a recitare. Zitto, zitto, sottovoce, piano piano, sottovoce, zitto, zitto, ma conviene, seguitiamo a recitare, 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 seguitiamo a recitare.
Principino, dove siete? Principino, dove state? Oh, perché m'abbandonate? Mi farete disperare. Io vi voglio, vi voglio.
Non diamo in bagatelle, ma non diamo in bagatelle. Ma invitarmi a due sorelle, tutte insieme non si può, tutte insieme non si può. Una sposa
E l'altra.
All'amico la darò. Sarò docile e amoroso. Tenerissimo di cuore.
Scudiero, no, signore, un scudiero, questo no. Con un'anima plebe.
Sarò buono.
Con un'aria dottina.
Amoroso.
Con un'anima plebe.
Sarò buono.
Con un'aria dottina.
Amoroso.
Mi fare,
La scenetta originale veramente da contare.